So yeah, welcome everyone to another week's intercontinental seminar on gravity and cosmology. This week we have the pleasure to host Professor Nicoleta Voicu from Transilvania University of Brasov, and she's going to talk about kinetic gases to an exponentially expanding universe. Please, Nicoleta, thank you very much for being here.
Hi, everyone, and really thank you for inviting me. First of all, I would like to mention that this is joint work with Christian Pfeiffer and my department colleagues, Anna Friedel-Sass and Elena Popovici-Popescu. And yeah, the newest part of it, actually, it was made during Christian's visit in our department. And here are the main ideas of the talk. First of all, we start from the idea that something is lost in the GR description of a gravitating kinetic gas. So we use gravitating kinetic gases to pass to an extended geometry, which is Finsler geometry. That is based on a more general notion of arc length than Riemannian geometry. And I will argue during the presentation that using Finsler geometry, we can really take full velocity distribution of the gravity sources into account. And the second idea is that, okay, now we pass to Finsler geometry, and it has quite some magic in it, in the sense that it, in cosmological symmetry, for instance, it determines not only the scale factor dynamically, but also the causal structure. The causal structure is more general in Finsler geometry than in Riemann geometry, so it allows for more freedom. And what we discovered, indeed, for the moment, just in vacuum, that we can have expansion in vacuum, which can be even exponential. So this is the most recent work on which the second part of the talk is based. The first part is based on some older papers of mine with Christian Pfeiffer and Manuel Hohmann from Tartu. Okay, so first part, let's talk a bit about kinetic gases. By a kinetic gas, I will understand a large number, say n, of interacting point particles, which are described by a smooth function depending on the positions and velocities of these particles. So by a large number n, I understand a number of particles that it's large enough as to consider these particles as a continuum. So it's in an in-between situation between really counting discrete particles and averaging all velocities and treating them as a fluid. So in a kinetic gas, we treat particles as a continuum, but we describe them using a scalar function depending on their positions and velocities. I will say in a few moments who exactly is this function. All right, so having a kinetic gas, freely moving particles move on geodesics, that's our assumptions. Moreover, on normalized geodesics, that's unit speed, meaning that this pair, consisting of positions and velocities of the particles, belongs to the so-called mass shell or observer space, depending on what you read. All in all, it's about the set of unit time-like vectors, which in Riemannian geometry or in GR is described as here. So it's a subset of the so-called tangent bundle, which is the set of allowable positions and velocities. And I'm using a plus minus 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 signature, then the norm of the velocity vector is 1, and x dot is assumed to be future pointing. So briefly, O is the set of unit time-like vectors. Now, the role of phi, which is called the one-particle distribution function, is to count the particle trajectories crossing a certain hypersurface in O. So this is the formula giving the number of particles. So in a sense, phi is density. So when we integrate it over a volume, we get the number of particles crossing that hypersurface, the boundary of that volume. And an essential assumption, since we have here a function which has to be integrated on something that usually is non-compact, we need phi to be, in principle, compactly supported, or at least integrable on each fiber. So at each point, we have the set of normalized for velocities, which is OX. On each set, as we approach the speed of light, the number of particles that have that speed is lower and lower. At some point, it has to become zero. So yeah, that's maybe you would say a drawback. We exclude ultra-relativistic gas. So we assume that we have really massive particles, mostly having small velocities compared to the speed of light. Now passing to gravity generated by a kinetic gas, the formalism is known in GR as the Einstein-Brasov equations. And it goes like this. Assuming that your source of gravity is a kinetic gas, you first build the energy momentum tensor of that gas, which is actually the second moment of the one particle distribution function phi. That means, formula like in form, you take phi, you multiply it by the mass of particles. So we assume that, okay, we have a finite range of masses. And if we have different masses, then we build such an integral for each mass. Multiply it by the velocity components, such as to get a 2-0 type tensor when you integrate. So that's how we built the energy momentum tensor. Needless to say that, okay, this means an averaging process. We scan all possible velocities around the point, and their contributions give you the energy momentum tensor. Then the energy momentum tensor is coupled to geometry via the Einstein equations. Here are some comments of mine. First of all, as we see in form, T mu nu is obtained by averaging over all four velocities. So it's a scheme like, say, passing from a kinetic gas to a perfect fluid in some sense. So in some way, we feel that we lose some information. And more precisely, in statistics, such a function is described by all its moments. So think of a reverse Taylor expansion, but not in terms of derivatives, but of integrals under some nice assumptions on differentiability, I don't know, compact support. A function can be recovered by its moments, which are in principle infinitely many. Okay, maybe not all of them independent, that's a separate question. But in order to recover a function phi, we need all its moments. Or these moments do not appear here when generating gravity via Einstein-Brasov equations. So here is probably a more precise description of this loss of information. So what to do? Want full velocity distribution? Then think Finsler. And here is the basic idea. We want to couple gravity directly to phi without averaging, like in the construction of the energy momentum tensor. And that's how it goes. Let's recall that the one PDF, the one particle distribution function of a kinetic gas, is a function of positions and normalized for velocities. But so is the fundamental geometry generating function of Finsler geometry. So what if we treat this as a dynamical variable? Then we are able to couple on the same footing phi and L. And what we get, okay, there's some technicalities here, build an action, vary it, we get a scalar equation depending on positions and velocities. And this is the gravitational field equation. We call it canonical because we like it. It's ours. Maybe some people would say that, okay, there are others. We will argue that that's the simplest one we can get from physical principles. So what we get is a field equation that works on the same arena as the one PDF. And this is the space of positions and velocities, technically the tangent bundle of spacetime. So M here is the spacetime manifold, which is four-dimensional, okay, connected, oriented, time-oriented, whatever you want to think, globally hyperbolic. So M is a four-dimensional manifold treated as space-time. Then Tm is its tangent bundle, non-technically the space of positions and velocities. And we denote by x mu x dot nu its local coordinates. Okay, so we talked about Finsler spacetime function, but what is this? So what's the notion of Finsler spacetime? Now, the precise, very technical definitions might vary in tiny details among authors, but all of us tend to converge that a Finsler spacetime is a pair consisting of our manifold, spacetime manifold, and a scalar function depending on positions and velocities, defined not on the whole tangent bundle, but on a subset with nice properties. It's assumed to be a connected conic subbundle. I'm going to explain what this is, with positive values, with three properties. So we have a scalar function, which is required to be positively homogeneous of degree 2 when rescaling the velocities. Then its Hessian with respect to the velocity has to be Lorentzian, and probably your intuition is correct, that will play a role which is quite similar to the one of the metric tensor in Riemannian geometry. It's less fundamental. The fundamental building block of the geometry is L, as you can see. G mu nu is a derived object, but it does play the same role, raising indices, lower indices, and also expressing geodesics, whatever you wish, curvatures then. So this is the second property. We want a Lorentzian metric tensor. And third, on the boundary of each Tx, so in each tangent space, we have a fiber Tx. On the boundary, we want L to be continuously extended at 0. And that already suggests who this T we want to be. T will be the set of future directed time-like vectors in physics. And now let's go to this notion. By a connected subbundle, we understand a set of positions and tangent vectors, velocity vectors, which is stable under positive rescalings of vectors. This we need in ensuring that this axiom makes sense. So L has to have certain properties when we rescale vectors. I'm going to explain in a few moments what this axiom ensures. And at each point X, we want the fiber, which is the time-like cone, to be non-empty. So we need to have at least one future pointing time-like vector at each point. Actually, what we obtain is a convex cone using these assumptions. Now, why do we require positive 2 homogeneity for L? Is because we want to build Ts squared via L. And here, using homogeneity, we can also obtain an expression which is largely similar to the one in GR and in Riemannian geometry. The difference here is that G mu nu depends on direction. Okay, another remark is that L is generally defined and smooth on a larger conic subset in Tm than T. No one forbids that, and these are then called admissible vectors. The details are that L is not necessarily positive, G is not necessarily Lorentzian outside T. Actually, in gravity applications, we don't care of what happens outside T and its boundary, on which we recall L has to be 0. So this is the arc length element. We can see here why it's more general than in Riemannian geometry, via this dependence on x dot, on G mu nu. But the rest is quite largely similar in terms of arc length and geodesics curvature. The length of a curve, we obtain it by simply putting the square root of L, or modulo of L if we go beyond T. And this is basically a similar expression to what we have in Riemannian geometry. Then proper time is defined just as in GR. So it's basically the arc length divided by the speed of light. That's a constant also ensuring the correctness of units. So, message to take home, Finsler geometry is equipped with the most general notion of geometric clock, the most general notion of arc length. And two homogeneity of L really ensures that tau, the proper time, is uniquely defined. So no matter from which local coordinate system, which parameterization you start with, for a certain trajectory, you get the same proper time. So that's two homogeneity. So we require, here I could have written, we require that proper time is uniquely defined. We require Lorentzian signature, that's a proper causal structure, and on the boundary of the set of time-like, future-pointing time-like vectors, we want L to be continuously extended as 0. Generally not smoothly. And here's where some authors required geodesics to be continuously extended. Okay, these are technicalities, so we stay minimal for the moment. We don't talk, for instance, about the past pointing cones. Okay, we can require also these. So how does the picture looks like? We mentioned the time-like cone. So this is how it looks like. It's a set where L is greater than 0, G is Lorentzian. Sorry if the picture is a bit small. Typically, L can be defined outside this set. We can have regions where it's negative, or G has a different signature. Maybe L is not smooth. What we are going to focus are these cones. And inside these cones, we have the set of normalized for velocities. So now the relation reads L equal to 1. And it's quite largely similar to what we have in Riemannian geometry. The difference is that piece of hyperboloid here is not necessarily quadric. And why am I saying this? Looking at examples of Finsler spacetimes, and more general examples of Finsler spaces, the basic idea is that Finsler geometry is Riemannian geometry without the quadratic restriction. That's a quote by Chern, back, I guess, in the 60s or even earlier. Looking at the examples, the first example is Lorentzian, or general pseudo-Riemannian geometry, which is characterized uniquely by the fact that it's quadratic in x dot. So for Riemannian geometry or pseudo-Riemannian, L is a quadratic expression in x dot. Here I denoted the Riemannian metric with A, not with G, to make a difference because later on we use it to compose Finsler functions. So think of A as being Riemannian metric. So coefficients of a Riemannian metric just depend on position, and here's the Finsler function associated with the Riemannian metric. Now, the most common ways of composing Finsler functions are either by deforming a Riemannian metric, pseudo-Riemannian metric via one form, like, for instance, in VSR metrics. These are called Bogoslovsky or M-Kropina metrics in the literature, or use two pseudo-Riemannian metrics, two Lorentzian metrics, and get something like a quartic L. So L is now the square root of a quartic polynomial in x dot. And this is, for instance, used in order to model birefringence. There are plenty of such examples. I just gave here 3. So here is the one-phrase description of Finsler geometry. This is Riemannian geometry without the quadratic restriction, in the sense that our metric tensor will be allowed to also depend on x dot. Not so much is different when we talked about geodesics. They are still described by an ODE system of degree 2, where these coefficients, called the canonical spray or geodesic coefficients, are generally expressed as in relation 15. So something like the Christoffel symbols contracted twice by the velocities. Again, the difference is that these Christoffels depend on x dot. Then the curvature, Ricci tensor, Ricci scalars are constructed largely similarly to Riemannian geometry. Same, just largely. There are some differences, but basically the idea is the same. Here is one more quantity which I'm going to use. It's called the geodesic or the Beeb vector field, which is the vector field on Tm, which is tangent to geodesics, actually to lifts, gamma gamma dot of geodesics. But just have in mind that R is tangent to geodesics, or its integral curves are geodesics. Okay, so this is in brief Finsler geometry. Now passing to kinetic gas action. This was built together with Manuel Hohmann and Christian Pfeiffer in 2020. The basic idea behind this is we look at the set of normalized for velocities with respect to a Finsler metric. We take a hypersurface. So the one PDF of the kinetic gas again describes the number of particle trajectories crossing a hypersurface. And now imagine that you have such a swarm of particles and you let them evolve, each one according to its proper time t, each one having its mass. So let's imagine now we have a swarm of particles of the same mass. And by the action, we understand the number of particles multiplied by their mass, multiplied by their time. So we just cut off the time at the value t. Then the time is given by this integral of ds, okay, the tau. So assume c is 1. And we can transform this into a volume integral, which is our action for the kinetic gas. So of course, if we have more masses, then we sum the actions for each. So this is our action, varying it, of course, also putting the left-hand side, the geometry part. R is the so-called Finslerian Ricci scalar. It's actually what you would think as the Ricci tensor in Riemannian geometry contracted with the velocities. And here division by L means that the velocities have to be normalized. So we just take into account unit speed, unit for velocities. So put geometry, put the matter action generated by the kinetic gas, we obtain the total action. And by varying it, we obtained a scalar equation on Tm of the form G is a constant, K times phi. Okay, the constant has to be determined just as in GR by passing, say, to Riemannian limit, Newtonian limit, and so on. Here is our G. It doesn't look very, very friendly. So here R is the Finslerian Ricci scalar. We have the usual Ricci scalar. So this is R mu nu in terms of Riemannian geometry, contracted by the inverse of G. So this is in some sense similar to what we get in Riemannian geometry. Here there's a totally new part. P mu is the so-called trace of Landsberg tensor, and here it's what it gives. So now our G depends on direction x dot, so our volume form given by this determinant of G also depends on x dot. P mu measures how this non-Riemannianity of the volume form evolves as we move along geodesics. So in a Finsler spacetime, we may experience in a sense different geometries. And this P keeps track on how dependent on direction is our volume form, how different these geometries are as we move along the geodesics. Okay, so this is our field equation. We already see that G depends on xx dot, phi depends on xx dot, so we don't average over velocities, but we can do that, of course. This means passing to moments, and the first thing we have in mind is, okay, build the second moment and see what we get. So what we can get, in the right-hand side, we get, again, energy momentum. Here I wrote energy momentum density, actually. And in the left-hand side, performing the same procedure, we get, so here L to minus, oh, it should have been L, not to minus 1. Sorry, this is a misprint. L is formal because on OX L is 1. Just wanting to underline that we normalize for velocities all the time. So what we get here is the second moment of G of the left-hand side, assuming that it's integrable, compactly supported. That makes sense. It's equal to the energy momentum density. So this is formally similar to the Einstein-Brasov system, but not identical. So here we don't have a Riemannian metric in principle. Okay, we can have, like, for instance, in cosmology, we can think of Friedmann-Lemaître and compare. What we most surely obtain are not identical equations, but they are formally similar. But what we have now is that we can build also all the other moments in a similar way. So contract G by n copies of the velocity components, we get the nth moment of G. Similarly, we can get the nth moment of phi, and these are proportional. What does it tell us is that the Finslerian approach captures the full velocity distribution of gas particles. So no information about the velocity distribution is lost. Okay, and you may ask, what's the relation between this fact and accelerated expansion? Actually, it's more subtle. It's not so immediately. Think of passing to Finsler geometry motivated by kinetic gases and wanting to have the full velocity distribution. But what we get is that our causal structure, our Finsler function L, is different. It's more general. And this is visible in cosmological symmetry. So passing to cosmological symmetry, a first mention is, again, we determined in 2020, starting from an axiomatic definition of cosmological symmetry. So homogeneity and isotropy having the groups acting transitively. We get that the generator of cosmological symmetry are nothing different from the ones in GR. So again, we have spatial rotations and spatial quasi-translations. And using the invariance of L under the flows of these generators, we find that L has a constrained form. So it can depend on the time t, on t dot, and on the spatial line element, which is nothing else than the spatial line element of a three-dimensional constant curvature Riemannian space. So if you look attentively at 22, it's actually the spatial part of Friedmann-Lemaître Robertson Walker metric in disguise. So really translate, instead of r dot, put dr, d theta, d phi respectively, and you get exactly the spatial line element of the Friedmann-Lemaître metric. So L is quite constrained. Here, using two homogeneity, L is t dot squared times a function of t and the ratio between w and t dot, which can be interpreted as spatial speed. So that's the most we can get. Now, how different is that from Riemannian geometry? Spatial slices have the same geometry. What is different is the more general intertwining between space and time. So in Friedmann-Lemaître metric, H is quadratic in S. It's in conformal time, it will be 1 minus S squared. In cosmological time, it's a bit different, but still you get the idea. It's quadratic in S. So in general, we have a non-quadratic dependence that's a more general causal structure. And the secret is that passing to a Finslerian framework, this causal structure is determined from the field equations dynamically. And since actually the field equation is super complicated, we assumed an ansatz that L can be described by separated variable. This boils down to having a conformal time. So having the scale factor taken in front as a common factor. So redenoting t by eta, so interpreted as conformal time, L has this form. So we assume from now on a conformal time ansatz. We assume that we have a conformal time. And our h now is a squared times some function that depends on s only. And here is a summary. Friedmann, Lemaître, Robertson, Walker metrics written in conformal time are given by this f. So f squared is 1 minus s squared. In general, yet f is completely arbitrary and is to be determined from the field equation. Then, writing the field equation, we needed a bit to use software because it's super complicated, yet it has a quite nice structure. So writing the field equation in conformal time, we got 24, which is some coefficient. Actually, k is spatial curvature here. So it's spatial curvature times some function that depends on s only, plus squared Hubble parameter in conformal time multiplied again by a function of s, plus h dot multiplied by the coefficient depending on s is equal to the right-hand side, phi. Here phi also depends on t and s. So from zero homogeneity in s, phi is originally determined on O. We can prolong it to t by zero homogeneity, meaning that along a direction, phi is the same. So here is our field equation in conformal time. Still super complicated, still we haven't found a realistic phi, yet we could solve it for vacuum, so for phi equal to 0. Well, prior to solving the vacuum equation, here is the form of these coefficients. It's quite complicated. So we still need some work to make sense of all these equations. Still, we need to use some ansatzes in order to ever find exact solutions, or we have to resort to numericals. What we could do so far are vacuum solutions. Here, the situation is not so bad. So let's see how does a Finslerian vacuum look like. This is also justified by the picture I put in the very beginning. So looking at the evolution of phi versus speed, spatial speed, there is a region. So since phi has compact support in each velocity space, there is a region where it has to be 0. So for a certain velocity range, we anyway will have vacuum solutions. So this is the first step to solve the general field equation. So let's do it. For vacuum, we can separate the time dependence. So the trick is we can differentiate by eta, we lose this term, and then we separate, differentiate again. We get this equation, which is of order 3 in h, and this can be integrated. Here is the first integral, which is first order, and we could completely integrate it in conformal time in general. So depending on the values, the signs actually of the integration constants so far. So here we have a first order equation and 2 integration constants. We have one more step, which will introduce one more integration constant. So for positive C2, we get H as a tan or the tanh or linear, which leads to a scale factor. Here caveat is eta is conformal time, not cosmological time, but we can still find some nice expressions. And for C2 smaller than 0, the expressions are similar. For conformal time, it's a bit complicated to for C2 greater or smaller than 0, passing to cosmological time gives quite nasty expressions in terms of integral. Yet for C2 equal to 0, we were able to find nice solutions in cosmological time. So passing to cosmological time via the usual relation, we find, depending on the values of C1, two types of solutions. So for C2 equal to 0, we found either exponential evolution. Here we have these parameters completely arbitrary on R. So okay, it can be shrinking or expanding exponentially depending on the sign of D1. Or if C1 is different from 1, we have a power law. Here it's nice to mention that as C1 approaches 1, say it's smaller than 1 and it grows, this power grows to infinity. So we really approach exponential evolution. So this is a first example of scale factor determined in terms of cosmological time, and we got something super nice. Namely, even in vacuum, we have an accelerated expansion with no need for any dark energy or extra geometric objects. All we needed was a more general line element to be determined dynamically from the field equation. Now, determining the causal structure, that's f of s, for the example that we found with exponential of evolutions, that's C1 equal to 1, C2 equal to 0. We assumed for simplicity that the spatial curvature is 0 based on observations that, okay, spatial curvature is most probably roughly equal to 0. Then the field equation simplifies, still not enough, so we could find no analytic solution so far. We could find yet a numerical solution. So we first took a power series ansatz. We took a perturbative approach to find the initial conditions. First, the coefficients, we found them by comparing to Friedmann-Lemaître. Then the next one really substituting into the field equation and going perturbatively. And then using these initial conditions, we fed it to Mathematica, and that's what we got as the graph for F. So with green, olive green, here's the graph for Finsler, Lemaître, Robertson, Walker F, which is square root of 1 minus s squared. The blue curve is the numerical solution, so we see that we have a bit of a larger value for the root S0, and also we plotted the Taylor expansion. And here is the picture that we got for mass shell or observer space, so set of unit future pointing time-like vectors. Again, we can see Friedmann-Lemaître and Finsler with blue, which is a bit more open, and also the light cones. And what we note is that for small values of S, the causal structures are nearly indistinguishable. Deviations appear for larger S. So all in all, what we found, at least for this case, is that for small speeds, we get the same geometry. And deviations really appear at larger values for S. So this is it. To conclude, we took the full one-particle distribution function of a kinetic gas as a source for its gravitational field. And we found that the most natural model is a Finsler geometric one. So the most natural framework is a Finsler geometric one. We proposed the model, building a concrete action for the kinetic gas, also a concrete action for the geometry part. I did not have the time to explain this. We started basically from the principle that in vacuum, the trace of geodesic deviation should be 0, and found the closest equation that is variational to that. And that's how we got the left-hand side, the geometry side of the equation. So we built a Finsler geometric model motivated by wanting to have the full distribution of velocities of a kinetic gas taken into account. Then we let geometry do its magic. The secret here is that both the time evolution and the causal structure of space-time are determined dynamically. we have more freedom in the causal structure than in Riemannian geometry. And this freedom actually allows for an exponentially expanding universe without the need of any extra quantities. Okay, with the caveat, for the moment, we determined it in vacuum, and the causal structure, we determined it only numerically. The equation is super complicated. What we plan to do next is find a realistic matter distribution and solve the equation. We are happy in the first stage to solve it numerically. And also, okay, find exact solutions. We are working on that. Of course, we have to use specific ansatzes. And let's hope we are lucky to find an ansatz that gives us an exact solution. And here are some references. The first two articles account for the first part of the talk, building the model. Here is a discussion of cosmological symmetry in the Finslerian setting, determining the generators and the most general cosmologically symmetric Finsler function. Actually, the most general cosmologically symmetric Finsler function had been determined earlier by Manuel and Christian, but then they postulated the generators. Here we determined them, starting from an axiomatic approach. Here there's a review by Zarbach and Tsanias on kinetic gases in general relativity. Here is a more mathematical approach with really all the technical details. And here's the last part, where we determine the exponentially expanding universe. And thank you for the attention.
Thank you very much, Nico, for the nice talk. Are there any questions from the audience? Yeah, I don't see any hands.
Maybe
I have
I have
another.
one.
Yeah, go ahead, Ruben.
You spoke mainly about cosmology. My question is basically, in space we have also black holes or neutron stars. Are there people working on that? Is there any ideas that somebody found some solution which could be, for example, equivalent to a Schwarzschild black hole?
Not yet. For the moment, we have some timid start on that, some shy start. For a class of metrics that are closest to Riemannian geometry, that's Burwald metrics. These are singled out in the class of Finsler metrics by the fact that they admit an affine connection. So their canonical connection, think of gamma of XX dot, actually descends in a well-defined connection on the base. That's gamma of X, just as in Riemannian geometry. That's kind of very restrictive. For that one, we proved that Ricci flatness implies Schwarzschild, actually, or flatness, complete flatness. But there's a caveat. Okay, we don't know. There may be non-Ricci flat solutions, even in that context. Then passing to more general Finsler metrics, we really don't know. So the domain is still very open to future works. So we have hopes that we can indeed model quite nicely this situation, but yeah, for the moment, we don't have any results on that. So there are prospects. We need more forces to work on that. It's really huge. Usually calculations are quite ugly. So we may have to rely on numericals.
Yeah, I saw the equations, so
yeah,
I can imagine that it will be very difficult. In any way, thank you very much for answering the question.
Yeah, so we hope in some years we will have some solutions. Let's see.
Are there any other questions? Yeah, there's one in the chat. Niba says,
Okay.
Since the kinetic gas is not fundamental, should the Finsler geometry be interpreted as the effective geometry experienced by the kinetic gas? If that's the case, how should we interpret the acceleration expansion solution?
Oh, yeah, good question. In a sense, yes, it could be. It's an intermediate expression between really taking into account a huge number of particles individually and the fluid approach, still I would argue that it's more fundamental than fluid, since we lose less information definitely than that. So how would we interpret it than Friedmann equations in GR? So yeah, we go to a bit more basic level than Friedmann equations, taking more of the information into account. That okay, we don't have the ultimate answers. So yes, in a sense, it's effective geometry, if you wish. So it's still a continuum. And that's how they, by the way, work in quantum gravity phenomenology using Finsler. It's still effective in that case.
Yeah, related to that, I was wondering, so apart from the modification of the dispersion relation, let's say, which could be, let's say, detected if there's any, are there any other observational hints that could distinguish between Finsler and Riemann geometry, for example? Like anisotropies or Lorentz violation, or I don't know.
Lorentz violation, yes, definitely. So we do
Okay.
have it, as we have it also in other models that go beyond GR.
Mhm.
Yes, so Lorentz violation is a thing. For the rest, okay, we have.
But is it like unique, or are the different Finsler geometries describe different, so give different predictions?
Different Finsler geometries give different predictions.
Yeah.
So starting from a certain type of violation of Lorentz symmetry, you determine a certain Finsler geometry or class of Finsler geometries.
Mm-hmm.
So we have flat Finsler geometry, which is passing from Euclidean or pseudo-Euclidean geometry to a vector space with a norm. And the variety of norms that we can have, or pseudo-norms in Lorentzian setting, is huge. So imposing the symmetry generators, the local symmetry generators, we can single out a certain type of norm, maybe a unique norm or a class of norms, and then we can let it evolve on a curved spacetime. So passing from flat geometry to curved geometry by imposing a certain type of norm in each tangent space.
Mm-hmm.
In GR, you impose pseudo-Euclidean geometry in each tangent space. Here, we have much more freedom, but indeed, a certain type of local symmetry will single out a certain type of Finsler geometry. So it's versatile.
Yeah, thank you. Any other questions? Yeah, if not, thank you very much again for giving the nice talk.
Yeah, thank you. And really sorry for mistaking the hour at first. Yeah.
No, don't worry.